issue about differentiating on manifolds and how to get around the existence of that sort of pesky little second derivative of the coordinate transformation. So to sort of start trying to think about the issues of differentiating on a manifold, I'd just like to always just go back to the basics, the first time we see calculus. Because that's really where we can get our intuition about ways that we can go around it. So this is how we define our derivative. We say that we take our derivative at a particular value t. We move a little bit ahead of t plus delta t. We take f at t plus delta t. We subtract f at t, and then divide by that difference, delta t, and take the limit as delta t goes to 0. So that's our definition of a derivative. So what's going to, what changes once we're on a manifold? Well, the first thing that changes is what do we mean by t? So on a manifold, we might expect that t might become a point because now we're not differentiating on the real line, we're differentiating on the manifold, and so therefore t plus delta t may well go to p plus delta p. And therein lies the problem, essentially. So there's various issues here. So what is delta p is a sort of first legitimate question. So on the manifold, we can move in different directions. So delta p now is not just a single direction. We can go in a whole, up to n, the dimensionality of the manifold, set of different directions. So we might think, okay, we want to have, we've sort of got an analog of the gradient. So maybe our df dt goes to df by dx mu. That's question mark. It's one thing we could do. We could say delta p has a direction, so maybe that's the equivalent of differentiation. The only problem with that as we've written it is it's specific to a particular chart, but we can get around this. But we can get around it by saying, well, okay, but df by dx mu has some free indices, so we don't say that df by dx mu has any geometric validity on its own. Instead, we mop up the index with our covector basis, coordinate covector basis dx mu, and call this whole thing the geometric object. So we would say this is df. So it's kind of like grad f in R cubed. Now, for functions, actually, we've done something sensible in this case. But of course, as we saw when we thought about vectors at the end of the first lecture, this is not necessarily okay once we move beyond functions. And so we have this same problem. I'm just going to write it down again because we're going to kind of use the expression. Once again, we've got this matrix, the second derivative of the coordinate transformation. So we can go on functions, but if we try to differentiate again, then we get problems. So this is really because delta p corresponding to delta, well, there's a couple of reasons. Delta p corresponding to delta x mu is not geometric invariant. And of course, the real problem is actually the top line of the definition. If we try and sort of replace f with anything other than a function, we're trying to compare vectors, or in this case, covectors, at two different points on the manifold. And one thing that we saw is that our tangent space is defined at a point, and therefore it's a different tangent space at p plus delta p. So we cannot directly compare or subtract, in this case, two vectors or covectors which live in different tangent spaces. Sort of obvious when you write it down like that, but I think you have to just, sometimes when you start off, it's not obvious why you can't do this differentiation, but as soon as you kind of think, well, no, it's a different space, I can't do that, it's not allowed, then it becomes more obvious. So there are three resolutions that I want to discuss. This is what we'll be looking at. Three possible get-outs. So the one you've already met is the connection. And the connection provides a way of relating the tangent space at p plus delta p to the tangent space at p. So what the connection does, so the tangent bundle, if you think about the two-sphere and all those tangent planes, that's just at the moment just a sort of set of all these different two planes with different orientations, if we think of them as embedded within R cubed. But each of these two separate planes, then there's no particular relation between them. What the connection does is it kind of provides a little glue between all these different tangent planes, and it says, okay, so this point in this plane is the same as that point in that plane. So we're kind of going to glue together those particular points throughout the tangent bundle. So that's what the connection does. The connection is a very general way of connecting tangent planes together that will work for any tensor in any circumstance. That's the plus, the minuses, it's extra structure. So that's what you know. What we're going to talk about today is the exterior derivative. The exterior derivative is going to be a way of eliminating this unwanted piece, the second derivatives, and it's going to do it by taking an antisymmetric derivative. So it's again, it's sort of stepping back in generality from the connection, because we're going to see that it's restrictive. We're going to see we're going to have to restrict ourselves to covariant tensors. We're also, in the end, going to have to restrict ourselves to antisymmetric covariant tensors. But it's also, it's got some generality in that it does, within that restricted set, it's still general. The final thing that I want to talk about is the Lie derivative, which requires the least structure but is the most restrictive, is a derivative with respect to a vector field. So in other words, it uses, you assume you have a vector field on the manifold, which is a means of linking points together. And once you've got at least locally, uniquely specified sort of set of curves which links points together, you can then kind of scooch your tangent spaces along those curves to do the comparison. So it's completely geometric, and it's sort of got no extra structure whatsoever. The disadvantage is it's absolutely tied to some background vector field. So So it's limited to a derivative along a vector field. So let's take each of these in turn. So we'll start by looking at forms and exterior derivatives. So we've said that we can define this thing called df. It's a rate of change of f, and it's a covector. So we can make a covector out of the derivative of f. So we're saying we're going to start by building this D by saying it's a map on functions, is a map from C infinity of M into C infinity of M, and then such that at a point P, df contracted with a vector is equal to Tf. Remember, that was how we defined our vectors, as the linear maps. And that is true for all T in Tp of M. So df is a geometric covector. It's a geometric object. And so now we want to extend D to cotensors. So, and we want to do it in such a way that we don't have issues with that symmetric second derivative of the coordinate functions. So to extend D, we've got a covector from a function, so we might expect a sort of second-rank covariant tensor if we take D again, but we also, if we don't want to have problems, it's got to be anti-symmetric. So we need to have a formal means of saying, what do we mean by these anti-symmetric tensors? So these are going to be our forms. So we say we've got a P form. And a P form is an completely anti-symmetric rank P covariant tensor. So that's what it is. And we build it up in the same way as we build up general tensors by taking tensor products. So we take sort of combinations, say, of vectors, and then that sort of builds our tensor product space. To get these anti-symmetric tensors, we use the anti-symmetric equivalent of a tensor product. And this is the wedge product, so we denote it by this little sort of hat thing. So to see, as always, when you first meet tensor product, you do a tensor product of two vectors. Here we're going to take a wedge product of two covectors, or one forms. And we simply say the wedge product is the tensor product, wedge product of A and B is the tensor product of A and B minus A and B reversed. So A wedge B here is a two form. And so we build up here. We've built it up, we've just done two rank 1 vectors, but in general, it leads to, if we now make them rank P and rank Q, so how do we take a general anti-symmetric product? We sort of throw, if we do this in index notation, and this is true whether it's abstract or not. We anti-symmetrize on everything, and that's our wedge product. But of course, there are combinatorial factors. Now, just remind me, Tibor, have they seen this notation?
I don't think so.
Okay. So there's a note. So okay. So then aside and aside on notation. So if you see Q, A1, AN, you see an object with...
I think Neil has done that.
Yep.
Yeah.
You happy? Yep.
Yeah. Sorry.
Okay. Well, then forget it. So that's the reason for these various factorials, because there's a, there's a P plus Q factorial on this sort of this anti-symmetrization here, and then of course, if you take permutations of these indices, you've got the subgroup which just permutes these lot, and because A is anti-symmetric, that's just going to give you A up to a sign. So that's where these bits come from. So note this is the wedge product is linear but not commutative. Now, it's sort of blindingly obvious that it's not commutative from the definition up here, but it's not necessarily anti-commutative. It depends on the rank of the forms. It's obviously anti-commutative for one forms, but in general, if I look at this A wedge B, where you've got a rank P and a rank Q, you get a minus sign. Sorry, it's B wedge. You sort of think about, you've got to pull all of these Q indices through all of those P indices, and every time you shuffle, take a permutation, you get a minus sign. So you only get a minus sign if the rank of each form is odd. Now, the other thing about the forms, these anti-symmetric tensors, is you can't go on ad infinitum. They can't be infinitely big. Because on a finite dimensional manifold, if you try and take a permutation of n plus 1 indices, 2 of those indices are always going to be the same. And if it's anti-symmetric, that tells you it's 0. So there's always a limit. We can only have forms with P less than or equal to n. So it's not a sort of open-ended thing. We've got a limit in terms of these this exterior algebra. So the n form is actually unique up to a factor. And it's a multiple of the alternating symbol. So the alternating symbol, remember, is basically epsilon. If we're in 4 dimensions, epsilon A, B, C, D is plus or minus 1 for, depending on whether you've got even or odd permutations of 0, 1, 2, 3. So it's just like the sort of standard epsilon symbol that you meet in 3D vector calculus, but in this case I've done it for n equals 4, but for however many dimensions your manifold has. Now, strictly speaking, this epsilon, this alternating symbol, it's, the way I've written it down, it looks like it's a tensor. It's not quite a tensor, but I just want to discuss it a little bit because it's kind of quite an important invariant tensor. So when you meet epsilon I, j, k in standard sort of vectors, 3D vectors, epsilon ijk is actually an invariant tensor. So it's one of the standard invariant tensors. You've got delta ij, chronica, and the epsilon symbol. And the reason, what's nice at least in our case, because we're doing general relativity, we want to have metrics, we can in fact make something which is geometric out of epsilon. So I just want to talk about that because it's something that crops up. So strictly, our epsilon here is a tensor density. So when people were building these contravariant and covariant rules for transformations of objects, tensorial objects under coordinate transformations, they also realized that as well as having these covariant or contravariant transformation rules, you could also get a weight of the Jacobian, the determinant of the coordinate transformation as well, that also it's not quite a straightforward tensor, but it's a tensor up to a weight, and that can be useful too. So we see if I define epsilon, and note you'll see my epsilon here is not curly for a reason. Now here I'm just going to, for the sake of convenience, I'm going to stick with 4D, okay? So I'm going to just look at, for the moment, I'm just going to think about this epsilon. Suppose I try and make a tensor, a sort of geometric tensor out of it. Then I do a coordinate transformation. And then I'm going to get dx mu by dx prime mu primed, etc. So the definition, if I look at this first expression, this is actually how you define the determinant of a matrix. You simply take n copies of the matrix with this alternating symbol. And so this is, in fact, det of dx by dx primed times and this is sort of looks like this second bit is sort of tensorial, or looks tensorial. And this is the weight, what's called the weight of the transformation. So what you see is that what my epsilon that I've tried to define almost looks like a tensor. You've almost got the right transformation, but there's a factor of the Jacobian in there. So that's the weight. That's the bit that makes it a density. Now, in our case, if we have a metric, then we in fact can define actually define a tensor. We don't have to sort of put up with it just being a tensor density. We can actually define a tensor which has the properties of being an alternating symbol, but it may not be quite plus or minus 1. It does swap sign when you swap the order of the indices, but it might not be plus or minus 1. So how do we do that? We define our, if we want to do it in components, epsilon A, B, C, D, again in 4D here. What I'm going to do is multiply by the determinant of the metric, take on the alternating symbol. So why did I do that? Well, under a coordinate transformation, Under a coordinate transformation, G transforms covariantly. So the determinant of G is a density. So the determinant of G picks up two factors of dx prime by dx. So det G is not a scalar. I mean, it's a number, but it's not a scalar. It's a scalar density, which means that the number does actually shift if you change coordinates. But it shifts in a very neat way. It shifts by the Jacobian. So that's why we take the square root of G here. The square root of G simply just has one factor of this transformation determinant, and you can see it's just one factor that we've got up there. So the whole thing actually goes together. So now, with that extra factor coming from the transformation for root G, I see that this curly epsilon symbol is, in fact, a tensor. So I've kind of played with my alternating symbol. I've given it a weighting, a sort of local volume factor, if you like. That's what it's going to turn out to be. And with the local volume factor, it's now a geometric invariant. So that makes perfect sense. If I have a metric's telling me about the local sizes, local distances. So if I take the determinant, that's kind of telling me about the size of a local little box, a local volume. And that ought to be, hopefully, something that's a geometric invariant. At least physically, it should be. We may disagree on how we label our volume, which the time part of it or the space part of it is, but we should agree on how big it is, because that's something physical. It's something that has a meaning. So we can also use a metric to jump between the space of P forms and the space of n minus P forms. So in this case, this star we call the Hodge dual, and it's a way of taking us, so we take our star A, our A is a P form, so what we do is we take our P form, we take our epsilon tensor, and then we use the metric, or the inverse metric strictly, to raise up P, the P indices. Well, in this case, I've raised P of the epsilon indices. And we're basically sort of taking the last P parts of the epsilon tensor and contracting those with the P form A. So this is a means now of hopping. First of all, we just had lambda naught, the functions, lambda 1, the 1 forms, lambda 2, the 2 forms, etc. But now we've got a way of actually talking from like lambda naught to lambda n, lambda 1 to lambda n minus 1, and so on and so forth. And basically, this Hodge dual is kind of the reason why we can do vector calculus in 3 dimensions, and why we never meet 2 forms till quite late on in tensor calculus. Because in 3 dimensions, we've got a map between our epsilon, our 3 form and a 0 form of function, and we've got a map between, by the Hodge dual, between 2 forms and 1 forms, or vectors. So a 2 form, where we're going to see that we pick up 2 forms quite commonly. The Maxwell stress tensor is a 2 form. In 3 dimensions, a 2 form, you can just Hodge it, star it, and it comes back to a vector. So it's kind of the reason why we don't see forms until, quite late on. So let me just, having set out my stall, I've told you what P forms are. I define D on functions. Let me now just sort of finish things off and say what D is in general. So mathematicians would define D by saying it was a map between P forms and P plus 1 forms that was sort of pseudo-Leibnizian, that it was a derivation. So I'll define it by actually writing down what it is in terms of the tensor, the index notation. So what you do to extend D, we want to take a completely antisymmetric derivative so that we don't get these yellow terms here. So we take a partial derivative of our tensor. Just the only thing to notice, I'll just pop it in blue, is notice that it's the first component here that is the differentiating index there. And we take the partial derivative of our tensor and then anti-symmetrize it to pieces, right? So that we sure that we never pick up those unwanted coordinate transformation terms. So we just note D reduces to partial differentiation on functions. So this is what I was saying before. D is Leibnizian, it's pseudo-Leibnizian in a way. So, and this is, of course, with derivation. This is kind of part of how you derive connections, supposed to be Leibnizian. They reduce to D as well. So what I mean by this is it's Leibnizian up to factors which take into account the antisymmetric nature of the derivative. So D of A wedge B is D of A wedge B, but then it could be minus if P is odd. So it's minus A or plus A wedge DB. So this is really thinking about the operator D here, acting on both A and B. You act on A. D then has to act on B, but to get to B, it's got to go through A. And A is a P form, so you get minus 1 to the P there. So that's kind of where that comes from. So it is Leibnizian, but it's Leibnizian with a possible minus sign. The other property it has is that D squared equals 0. Now, it's obvious from the way I defined it using partial derivatives that that is the case, because partial differentiation is symmetric. But again, if you were defining it mathematically, you'd define it via that bottom bit, which is more a statement of how it behaves, reduces to this partial differentiation on functions. It's a derivation, so it's Leibnizian, but it also has d squared is 0, and it's this map from lambda p to lambda p plus 1. That's enough to uniquely specify it and exactly determine that this is what it is with respect to some local basis. So once again, using our Hodge dual, we can take the sort of dual of D. We can say, well, I can do D on a P form, or I can star my P form. Takes me to an n minus P form. I do D on that. That takes me to an n minus P plus 1 form. I star back again, and that takes me to a P minus 1 form. So delta is our sort of dual of D. So it's star D star, and it maps lambda P to lambda P minus 1. And so if I write it again in this abstract index notation, or just using some local basis, A goes to up to a minus sign, the divergence of A. So remember, this star requires a metric, so it's not surprising that you should see the covariant derivative come in here. So in this case, the covariant derivative is the metric connection. So what you're familiar with in 3D, the gradient of a function, so let me just write this down, is df. So that's, I said, the star was what enabled us to do vector calculus in 3D. So the divergence of a vector is now actually, let me get this right, it's going to be delta of v. You can sort of see that from this, no, where's it gone? Lost the plot here. Oh, there, right here. See it from that bit. And then, of course, curl of a vector is where we would have expected a 2 form, dv. We star it to get a 1 form, or a vector, and so that's why curl works. But it only works in 3 dimensions.
Question. Is the delta, the dual derivative, it's a derivation still?
It's a derivation, yeah.
It also has Leibnizian.
Yes, yes, absolutely. It inherits it from D.
Correct.
So the obvious physical example that I'd just like to cover to illustrate forms is electromagnetism. So I know you've obviously done Maxwell's theory. And we define electromagnetism. I mean, this is one of the really nice things that you do with basic special relativity. You can come and redo Maxwell's theory of electricity and magnetism, and you find it has this lovely expression in terms of 4-dimensional, vectors and a 4-dimensional gauge theory. So this is something that I think Einstein was particularly pleased about with special relativity. So it's a gauge theory, and our gauge potential, A mu, is defined as a combination. We've got our electric potential, electrostatic potential, and our vector potential. And from them, we combine and make a 4-vector or 4-covector potential A mu. So this is a 1 form in the language that we've just been using. So let's have a look at D of A. This is what's going to be our field strength. So if I take D of this object and write it down as matrix, well, we're taking antisymmetric derivatives. So if I look sort of along the top line, if I look at the derivatives of the 0 component of A, this is going to give me the gradient of phi. So that's sort of essentially going to give me the electric field. Now, for the space pieces of F, if I look at 2 spatial components here, that's going to be some spatial derivative of a spatial component of my 4-vector A. And so it's going to, sorry, I've just realized I've used A here as a vector, 3-vector, and here this is the 1 form. Then the spatial components of the 1 form are just the vector potential in the sort of standard Maxwellian notation, but we're taking an antisymmetric derivative. So for example, if I focus in here on this component, it would be, it's the sort of xy piece, and so it should be dx of ay minus dy of ax. And of course, we know by thinking about curl that that is indeed the 3rd component of curl of A, which is B3. So that's where we pick up those components. So the field strength, which when Maxwell wrote down, I think he didn't even write it down in a 3-dimensional vector notation. I think he wrote every single equation out, didn't he? So he had to write down loads of equations. Here, we've written down this. And it's a very simple way of encoding the field strength. So we automatically get half of the Maxwell equations. Because d squared is 0, df is d of dA, right? So that's 0. We've got gauge invariance. For the same reason. If I say that A goes to A plus d lambda, where lambda is some function, then I take f. Well, f goes to f plus d squared lambda, but that's 0. So f doesn't change. So the fact that d squared is 0 gives you both gauge invariance and half the Maxwell equations for free. So that's kind of a, a nice example of forms in action. And I'll just wrap up by so although in 4 dimensions, we could actually have higher forms and field gauge theories with higher form fields. But once again, because we're in a relatively low number of dimensions, we don't see it this way. So I'll just give an example and then explain why we don't see it this way. So here's an example of a gauge potential, two-form gauge potential. B mu nu. So it's a two-form, it's antisymmetric. And I'm saying that it's a bit like A. So my gauge symmetry is B goes to B plus dA. So A here is a one form. My gauge invariance. And then my field strength H is D of B. So if I wrote it in components, it would just be the, given in terms of the linearly independent partial derivatives of B. So this is, I mean, we could actually do a two-form in 4 space-time dimensions. But the reason we don't usually see this is, here's our field strength. Usually, it's an oversimplification to say that the physics is only in the field strength, because you can have little subtleties about sort of global effects in your gauge potential, particularly if your space-time has non-trivial topology. But let's just say, simplistically, in the simple case, the physics is all in H, or F, in the case of electromagnetism. So that was why it was such a leap for Maxwell, when he started putting down the gauge potentials. Really, initially, we saw electric field, magnetic field. So the physics is in the field strength. So here we've got a 3-form field strength. Well, in 4 dimensions, 3 forms dual to 1 form. So we've got a vector, which is a field strength. Well, what does a vector derive from? If I thought of it being d of something, it derives from a function. So really, our 3-form field strength is really coming from a scalar, actually, strictly speaking, a pseudo-scalar, because of the, the root g part in the Hodge dual. But that's why we don't usually meet this in 4 dimensions, because we always keep things as simple as possible. We wouldn't use a 2-form, we'd use a scalar. So let me just finish with a couple of... Why am I telling you about this, in other words? So in 4 dimensions, H is dual to d phi, say. So our 2-form is equivalent to, we can do a canonical transformation to make our 2-form into a scalar. So I don't know whether you've done this yet or whether it'll be coming up, but this is the axion particle. So this is what, this may come up or may have already come up in the standard model. So if it's about to come up, this is a point of reference you can come back to. So the axion is an example of one of these things. But really, where it crops up is of course, comes up in string theory, because the B mu nu actually couples to a line source. So why is that? Okay, so you've already met the fact that particles trace out world lines. So we saw that as a notion of a curve, but we could also think of that as a one-dimensional submanifold of our manifold. So a string is something that has an extension in space, one-dimensional in space. And it moves in time. So our x mu now depends on two coordinates, t and s. S is our space coordinate, t is the time coordinate. And so now we've got a two-dimensional submanifold of M. So as we will be seeing that we can keep going, higher dimensional submanifolds, but let's stop here for now. So A mu corresponds to a point charge. So our world line here, x mu t, can be a world line of a charged particle. And from a Lagrangian perspective, we encode that by saying that our particle, we add a term to our Lagrangian, which is the dot, the tangent vector combined with the gauge potential. So with strings, you get the same picture, but of course the string's now a world sheet, so you can't just charge it with a simple one-form gauge potential. So here's our world sheet. What does it mean, charged world sheet? Well, what we do is we take b mu nu, x dot mu, x primed mu, where x primed is now d by ds, the space-like direction. So we've still got a sort of b naught going along with the time direction on the world line, on the world sheet. But we use the extra leg, the extra index of b mu nu to mop up the derivative with respect to s. So we're kind of taking, what we're really doing here is we're taking a fundamental area form on our two-dimensional world sheet and saying that's a charge. So this is why when you start doing higher dimensional gravity and you're thinking about the implications of, or possible implications of string theory in terms of effective lower energy physics, this is why you start getting these higher form fields, because this b mu nu field, this sort of, think of it as a charge of the string, that actually is something that appears in the fundamental string action. I'm giving you the space-time picture here because that's what we're doing in this course, space-time physics. But this is something that we'll probably come back to, and it's something that's a little bit strange and a bit new. We're going a bit off-piste here. You're very familiar with sort of standard gauge potentials, but I'm just saying once you start looking at manifolds in more generality, you start finding that you can get a whole host of new things going on. Okay.